Ever pondered why like charges repel and unlike charges attract? Today we're going to unravel this mystery. Let's start at the very beginning. Everything in the universe is made up of tiny particles called atoms. These atoms are composed of even smaller particles, some of which carry a charge. Depending on the kind of particle, this charge can be either positive, like in the case of protons, or negative, like in the case of electrons. Now imagine two electrons, both carrying a negative charge. When they come close to each other, something interesting happens. They start to push each other away. But why? Well, it's because they're both negatively charged. They have similar electric fields that interact in a way that pushes them apart. This is the principle of like charges repelling each other. You can think of it as two similar magnetic poles that also repel each other. On the other hand, let's consider a proton and an electron, one with a positive charge and the other with a negative charge. When they come close, they don't repel each other. Instead, they attract. This is because their electric fields interact in a way that pulls them towards each other. Just like opposite magnetic poles, unlike charges attract each other. These interactions between charges aren't just random. They follow a set of rules or laws, one of which is Coulomb's law. This law explains that the force between two charged objects is directly related to the product of their charges and inversely related to the square of the distance between them. So, the next time you see two balloons repelling each other after being rubbed against your hair, you'll know it's because they have like charges. Now let's dive deeper into why like charges repel. Imagine two positively charged particles, or if you prefer, two negatively charged ones placed in proximity to each other. The invisible yet potent force fields surrounding these charges come into play. This is the electric field. It's like the personal space around us. We all have it, and we all like to keep it to ourselves. As these like-charged particles approach each other, their electric fields start to interact. It's as if they're saying, "Hey, you're encroaching on my personal space." And just like we would, they push back against each other. This pushing back, this resistance, is what we observe as repulsion. Remember, an electric field is simply a region around a charged particle where an electric force is experienced by other charges. So when two like charges come close, their fields push against each other, causing the charges to move away or repel. It's a bit like trying to push the same poles of two magnets together. They resist and push back. Now you might be wondering, why do these fields interact this way? That's a great question. The answer lies in the very nature of electric fields. These fields are vector quantities, meaning they have both a magnitude and a direction. For like charges, the directions of their fields are such that they resist or push back against each other. This is a fundamental rule of nature, a principle that governs the behavior of charged particles. It's not something that happens sometimes or under certain conditions. No, like charges always repel, no matter what. So to sum up, like charges repel each other because their electric fields interact in a way that pushes them apart. They're like two strong-willed individuals, each asserting their own space, refusing to be pushed around. Next time you see two like charges repelling, remember it's not a fight or a contest. It's just the natural behavior of electric fields, each asserting its own space. So, it's the battle of the electric fields that causes like charges to repel each other. But what about unlike charges? Why do they attract? Let's dive into this fascinating question. When we talk about unlike charges, we're referring to one positively and one negatively charged object. These two charges are like the ultimate romantics of the atomic world, always seeking each other out. But why? Well, the answer lies in the interaction of their electric fields. Just like an invisible bond, the electric fields of these charges reach out to each other. This interaction pulls the charges towards each other, creating an attractive force. It's kind of like when you try to bring the north pole of a magnet close to the south pole of another magnet. They just can't resist each other and snap together. The positive charge has an electric field that radiates outwards, pushing against everything it encounters. On the other hand, the negative charge's electric field pulls everything towards it, like a cosmic vacuum cleaner. When a positive and a negative charge get close to each other, their electric fields start to interact. The pushing field of the positive charge meets the pulling field of the negative charge, and they begin to pull towards each other. It's like they're playing a grand game of tug of war, But instead of one side winning, both sides pull towards each other, creating a perfect balance. This is why unlike charges attract. They're trying to achieve a state of equilibrium, a balance of forces, and they do this by pulling towards each other. So what we see as an attraction between unlike charges is actually a game of cosmic tug-of-war, where both sides are equally strong and equally determined to win. This interaction is a fundamental principle in the world of physics and is at the heart of many of the technologies we use every day. Remember, like charges repel each other, trying to push away from the pressure of similar electric fields. But unlike charges, they're all about the pull, the attraction, the cosmic tug-of-war. It's as if the electric fields of unlike charges are playing tug-of-war, and both sides are winning. All these interactions of charges follow a specific law, known as Coulomb's law. Let's dive into this fascinating set of rules that governs the world of charges. Named after the French physicist Charles-Augustin de Coulomb, who first published it in the late 18th century, Coulomb's law is a fundamental principle of electrostatics. It describes the force between two charged objects, providing us with a mathematical understanding of why like charges repel and unlike charges attract. The law states that the force between two charges is directly proportional to the product of their charges. This means that if we were to double the quantity of charge on either of the objects, the force between them would double as well. If we triple the charge, the force would triple, and so on. This direct proportionality explains why a larger charge results in a stronger force of attraction or repulsion. Interestingly, the force is not just dependent on the charge. Coulomb's law also tells us that the force is inversely proportional to the square of the distance between the charges. This means that if the distance between the charged objects is doubled, the force between them becomes a quarter of its original value. If the distance is tripled, the force reduces to a ninth of its original intensity. This inverse square relationship is why charges have to be close to each other to feel a substantial electrostatic force. Coulomb's law is expressed in a mathematical form as F equals K times Q1 times Q2 divided by D squared, where F is the force, Q1 and Q2 are the magnitudes of the charges, D is the distance between the charges, and K is a constant known as Coulomb's constant. The beauty of Coulomb's law lies in its simplicity and universality. It elegantly captures the fundamental principles of charge interaction, providing the backbone for our understanding of electricity and magnetism. In essence, Coulomb's law is the rule book that charges follow in their game of attraction and repulsion. Next time you see a spark or feel a shock, remember, it's all part of the fascinating world of electrostatics, governed by the simple yet profound Coulomb's law. So let's summarize what we've learned about the behavior of charges. We've delved into the fundamental principle of electrostatic force, discovering how it governs the behavior of charges. We found that like charges repel each other. This happens because two positively charged objects or two negatively charged objects have electric fields that interact in a way that pushes them apart. It's just like how similar magnetic poles repel each other. On the flip side, we learned that unlike charges attract each other. This is because a positively charged object and a negatively charged object have electric fields that interact in a way that pulls them together. It's akin to how opposite magnetic poles attract each other. We've also unraveled the mystery of Coulomb's law, which describes the force between two charged objects. It states that this force is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. In simpler terms, the closer the charges and the larger they are, the stronger the force between them. This law helps us understand why like charges repel and unlike charges attract. When two objects carry the same type of charge, their electric fields push against each other, causing repulsion. However, when the objects carry different types of charges, their electric fields pull towards each other, resulting in attraction. In essence, the interaction of charges is not just a random occurrence, but a phenomenon strictly governed by the principles of physics. It's a fascinating dance where the electric fields of charges interact, following the rhythm set by Coulomb's law. So whether it's the static cling of your clothes fresh out of the dryer, or the spark you feel when touching a doorknob, it all boils down to the principles of electrostatic force and Coulomb's law. So, the next time you see charges interacting, remember it's all just a game of field interactions and following Coulomb's law.